Well, good evening. Welcome to an exciting lesson about calculus. Here I am in my beautiful house, sitting with my lovely wife and my brother who's visiting. So let's get stuck into the chain rule. Who's excited? I'm so excited. I am going to add a rainbow pen. Hooray for calculus. Okay, now we've got that out of the way, let's talk about what we actually need to do, which is the chain rule. So it's a tool. We're going to be adding tools to our techniques for differentiating, finding the gradient function of a particular function. And one of these techniques is called the chain rule. So basically, if you have anything that looks like this, I'll draw a couple of examples in blue. If I had something like this, x squared plus 4x to the power of 6, well, currently you don't know, and we don't really know how to expand to the power of 6. But if I didn't have the chain rule, I'd have to somehow expand it and then do each term one at a time. But if I have the chain rule, I could differentiate something like this, the cube root of x cubed plus 3x, without any trouble at all. So that's what we're going to get into today. Now, proper terminology, if I have f of x to the power of n, and I want to do d dx of that, as in differentiate it, then what happens? The n, the power, comes out the front, and the f of x stays the same inside, but then we multiply it by the derivative of f of x. So it's the product of derivatives. You're kind of thinking about it as moving outwards in. You deal with the power of n of the whole function first, and then I've actually made a mistake here. That should be n minus 1. So you try to prepare beforehand, and what happens? N minus 1, and then it times f dash n, x. Okay, another way to think about it is if I have this big function, right, f of x, if I put a little arrow, d dx of that is equal to, well, you do the derivative of the bigger function first, leaving little f of x the same, and then you take that out and you multiply it by f of x. That's kind of what we're doing. So let's have a go at some examples, because that's going to illustrate the point, I think, the clearest. So here we have y equals, or f of x equals 4x plus 1 to the power of 4. Okay, now, well, how do I do it? I don't want to expand it to the power of 4. I'd have to do squared and then squared, and that's going to take ages. So we don't want to do that. So let's say we want to do dy dx. I'm going to call that dy dx is equal to, so here we've got a power of 4. Now what I'm going to do is keep what's inside the brackets the same. Think of it as a single thing, like call it a big X or a U or something. But think of it as just a single variable. Now, how would I differentiate that? Well, I'll bring the 4 down, just like we've been doing. What's inside the bracket stays the same. The power reduces by 1, but I'm not done yet. I have to then multiply this by the derivative of what's inside the brackets. That's my little f of x. So in this case, this example, looking back to what I was doing before, the big F of something is, if you like, u to the power of 4, and my little f of x is what's inside the brackets, 4x plus 1. Now, what's the derivative of 4x plus 1? Well, 4x, the derivative of that is just 4, and 1, the derivative of 1 is 0, so we don't need to write that. Now, if I bring it all together, this becomes 16 4x plus 1 cubed. There we go. So making something that was just a day ago quite complicated, now suddenly it is quite easy to do, hopefully. Okay. Now, as when we looked at fractional and negative indices, we want to avoid them in their fractional form, or when it's 1 over something, we want to have a negative index so that we can deal with it. So this one here, so let's say that's f of x. So I'm going to do f dash x is equal to, so we've got this negative 3 here. That's my power that comes out the front. Bracket. What's inside the bracket stays the same. That's like my input. Then my power is reduced by 1, so that's minus 4, times the derivative of what's inside the bracket, the next level in, if you like. We're working outside in. The derivative of 3x minus 2, well, that is just 3. Now this becomes negative 9, 3x minus 2 to the power of negative 4. Now typically though, we don't want to leave things as answers in negative. We want to kind of have positive powers. So this is going to become minus 9 times 1 over 3x minus 2 to the power of 4, which is equal to negative 9 over 3x minus 2 to the power of 4. Okay, that's good. Now, a question like this, for instance, let's say, just as a note, if I had something like 2 over 4x plus 5 to the power of 5, well, I would just rewrite that as 2 outside of 4x plus 5 to the power of negative 5, and then you could differentiate. Well, we might as well go ahead. F dash x is equal to, well, negative 5 comes down, we multiply it by 2, so it's going to be negative 10. What's inside the bracket stays the same, to the power of negative 6, times the derivative of what's on the inside, which is just 4. So this is going to be negative 40, 4x plus 5 to the power of negative 6. And using exactly the same principle as what I had over here, this becomes minus 40 over bracket 4x plus 5 to the power of 6. Not too bad, hopefully. Now remember, I'm doing a bit of a plug here on Canvas. If you don't know a question, put it on the discussion board or open up a new one, and people can be looking and hopefully will answer your question as well, or ask someone in class. Okay, let's do this one. X squared plus 2x all to the power of 5. Okay, well, let's do this. We're going to do d dx. Okay, remembering that that just means the derivative of x squared plus 2x to the power of 5 is equal to, again, the power of 5 comes down outside of what's inside the bracket, no matter how complicated, it always stays the same. Reduce the power by 1. Then we multiply by the derivative of what's inside. Well, the derivative of x squared is, I need to put this in brackets, 2x. The derivative of 2x is plus 2. Now, I just kind of clean this up. Usually we go left to right in ascending powers, so I'm just going to kind of write it like this, but it doesn't really matter. You can have it whatever order you like. And there we have it. Nice and straightforward using the chain rule there. Okay, now last little one here. Well, what's going on here? We've got 2 outside of the square root of x squared plus 3x all to the power of 3, or cubed, right? So, well, I'm going to say y dash is equal to, but before I differentiate, I need to get this into a different form. And I'm going to use fractional indices. Remember that this is equal to 2 bracket x squared plus 3x to the power of, the denominator of my fractional index is the root, so it's a square root, so it's 2. The numerator of my fractional index is the power, which is 3. Okay, so I've got 3 on 2 is my power, so now I'm going to sort of deal with it. Now when I differentiate, what happens? The power, 3 on 2, comes down. So it's going to be 3 on 2 times, now the 2 is still there, so I'm just going to keep it there, times what's inside the bracket stays the same. Then it's going to be 3 on 2 minus 1. Okay? Times, well, what's the derivative? What's the gradient function of what's on the inside? Well, x squared, the derivative is 2x, and 3x has a derivative of 3, and so we have that. So now if I do it, it's equal to, what's 3 on 2 times 3 is just 3. I'm going to bring that 2x plus 3 over here. Now this is x squared plus 3x to the power of 1/2. Now again, typically we don't like to see fractional indices in our final answer, so I'm going to write this as 2x plus 3, and then the square root of x squared plus 3x. So with a bit of care, a clear understanding about negative indices, how it works with fractional indices and how we can convert between the two, the chain rule is all about moving from the bigger function to the inside function and multiplying it. Basically, you're thinking of making a chain of derivatives, doing it correctly as they connect. All right, exercise 8.5. See how you go. And enjoy. See ya.